Today I'll be talking about logic-based explainability in machine learning. This is an effort that we started 3 years ago. And essentially, the objective of the talk is to give you an overview of what we have done. So everybody is familiar with the many successes of machine learning, from self-driving cars, the AlphaGo, AlphaZero, and AlphaGo Zero developments by DeepMind, image and speech recognition, personal digital assistants, robotics, and so on. One problem of some of these systems is that their operation is usually opaque, or they behave as black boxes. And so the objective of explainable AI is to help humans understand the actions of machine learning models. And this raises several questions. So how can we make these explanations understandable by humans? How to answer why questions, so why this prediction? And also how to answer a why not question, why not some other prediction? So for example, in a bank loan, how come I did not get a bank loan, and what should I do different to get a bank loan? And another question, important question, is do we have any guarantees of rigor? And there are other questions that I will be talking about as well. How can we list different enumerations? How can we check if some important feature like age, for example, is used in an explanation, and so on? And I will also briefly mention links with robustness, fairness, and learning. Now, the importance of XAI cannot be overstated. There is, at least in Europe, there is a GDPR. There are people stating that if given GDPR, people are entitled to explanations in general for algorithmic decision making. There was an effort by DARPA a few years ago on XAI. There is a recent proposal on how to use AI in systems that affect Europeans, at least again. And again, different authors have put the case that intelligibility or explainability is fundamental for people to understand even what machine learning models are doing, and even in the case if they have bugs, for example. Just another example of ethics guidelines for trustworthy AI in Europe. This is a fairly large document, but one of the things it is requested is the principle of explicability. So the ability for a machine learning system to be understood by human decision makers. And of course, there are, I would say, even more than tens of thousands of papers, or even hundreds of thousands of papers on XAI. So just going back to one of the regulations that I mentioned, in Europe, again, at least, the people have proposed a categorization of risk for AI systems. There are systems of minimal risk, limited risk, high risk, and unacceptable risk. So systems of unacceptable risk, systems of AI cannot be used. We are interested in systems of high risk where AI can be used, but its use must be understood and justified and explained. Examples include law enforcement, management and operation of critical infrastructure, biometric identification, and, for example, creditworthiness. Many other examples. Besides high risk, we also have safety critical uses like self-driving cars, autonomous vehicles, and so on. And so, and because of this, some authors have argued that the machine learning models should be interpretable from the outset. This is a well-known paper by a very well-known author on the topic. And in all these cases, explanations should be rigorous. So correctness is paramount. This is important to build trust, to help debug in case there are bugs, and to prevent accidents as well. And there are lots of examples of accidents in recent years. And so this is the motivation for the work we have been doing. Just again, a brief overview of the work that has been done over the last 3 years. So we started by trying to understand what an explanation was. And then we identified islands of tractability, so problems that could be efficiently explained. Then we devised efficient solutions. We focused on different queries, and I'll talk about this, input distributions, probabilistic explanations, and so on. So this gives you a distribution in time of the topics that have been covered by formal explainability. So this leads us to the topics of the course. So many topics, but some of them are short. So the first part until the break is we'll well, this motivation that I just finished, the preliminaries, and then formal explainability. What do we mean by this? How do we compute explanations, the very basic ideas, and then after the break, how do we, well, in more seriously compute explanations? What examples of tractable explanations are there? And then delve into explainability queries, probabilistic explanations, and a wrap up. Okay, so let's start with topic number 1. So in all the talk, I'll be always talking about classification problems. So it's a classification problem is characterized by a set of features, and each feature takes values from some domain. For example, gender can be, you can be male or female, as an example. Features can be categorical, as I just illustrated, discrete or real value. And feature space is the Cartesian product of the domains of the features. Besides features, we have classes, and a bunch of classes. And the machine learning model computes an interesting, so non-constant classification function from feature space to the set of classes. And besides this concrete classification problem, we are interested in what is called an instance. So we have a point in feature space, point V, with a given prediction, C, which is a class. And the goal is, how do we compute explanations in this case for this concrete instance? Some examples. I'll talk about lots of different examples. This is just an example of rules, in this case, an order. So the set of features in this case is 1, 2. The domains could be real value. We are predicting 2 different classes. And if the summation of the values of the features is greater or equal to 0, we predict plus, otherwise we predict minus. Okay. Another example, we will also see lots of decision trees. This is I will talk more later about this decision tree. It is from a book. So here we have 3 features. I will call them 1, 2, 3. It doesn't really matter. So they are length, thread, and author are the features. And the classes are skips and reads. And then we have the domains for the different features. Okay. As I said at the outset, if you have any question, please do ask. Okay, so let's talk a little bit about the logic background. So I'm going to assume you have seen this. Again, I'm not going to use SAT solvers or SMT solvers or and so on, but it is implicit that we can use them in some applications. So SAT is a decision problem for propositional logic. SMT is a decision problem for fragments, usually decidable fragments of first order logic. Mixed integer linear programming is extremely well known as well, and we can also use constraint programming. Again, if you are not familiar, there are lots of tutorials. This is a tutorial that I helped to put together, so you can actually 2 tutorials that I helped to put together. So again, usually throughout the course, I will talk about variables and literals, well-formed formulas. There can a clause is a disjunction of literals, a term is a conjunction of literals. A conjunction in normal form is just a conjunction of clauses, or disjunction of literals, and the disjunction normal form formula is a disjunction of terms. And again, this is the very basic. We can can generalize to more expressive domains. So another concept that is going to be implicit in some of the things I'm going to talk about is entailment. So if a var is a formula defined on some feature space representing some function, we can suppose we have another formula tau, and we say that tau entails phi if, and this is the notation, if for any point in feature space when tau is true, then phi is true as well. So a concrete example, this is my function. This is the feature space. And it's easy to see that if x1 is 1, then the form is true. And if not x1 is true, then the form is true as well. Okay. And another example, so a more complicated example, a larger feature space. This is the definition of my function. And so x1 and x2 clearly, if it's true, then the form is true. x1 and x3 is, if it's true, then the form is true as well. Okay. And we can generalize this for non-Boolean feature spaces as well. Again, we'll mention this when necessary. We'll also talk about prime implicants and implicates, mostly prime implicants. So conjunction of literals. Again, we will see conjunctions and as sets of conjunctions of literals as sets of literals where helpful. In this case, it is helpful. So a conjunction is a prime implicant of some function if it entails a function. and any subset of that of that set of literals does not entail the function. So a concrete example here, again, we know that this, we saw this before, so this is my function. We know that x1 and x2 entails the formula, yes? And, but we know that x1 does not entail the formula and x2 does not entail the formula, so this x1 and x2 is a prime implicant of the formula. And we can similarly define the junctions of literals as a prime implicants with a very similar way, okay? So it is often convenient to reason about inconsistency. So what we do is that we create formulas that are inconsistent and then we reason about them. So we start with some formula that is the conjunction of two different formulas. One is my background knowledge. We call usually them the hard constraints. And we have another one, S, which is the additional knowledge, which will be inconsistent with the background knowledge. We call them the soft constraints. And it is the case that the two formulas are inconsistent. So for example, here, if this is my background knowledge and these are my additional knowledge, my soft constraints, it is clear that the two together are inconsistent. So for example, the first two clauses here with this one will be inconsistent. The first and the third one here will be consistent with the second clause here. So a minimal unsatisfiable subset is a subset of the additional knowledge that is by itself inconsistent with the background knowledge. So I pick a subset such that the background knowledge with that set is still inconsistent. So in this case, just the first two clauses is enough to reveal the inconsistency. A minimal correction subset is a subset minimal set such that if I take those clauses out, I recover consistency. So for example, if in this concrete example, if I remove this one, so it's no longer here, then I just need to put x1 equals 1 here and here, x3 equals 1, and x2 equals 0, and that's it. Okay, so this is an example of a subset minimal or a minimal correction set. A well-known old result is that MUSs are minimal hitting sets of MCSs and vice versa, and I will mention this later as well. And then we can talk about variants that are extremely well known. So smallest size or cost MCS is the complement of maximum satisfiability. And people have also investigated smallest or smallest cost MUSs. Okay. So of course, many people in the audience will be saying, come on, where is the machine learning? So let's talk a little bit about machine learning. So this is an example of a neural network, and we'll see this example several times. So these are my inputs, some bias. I have, of course, it's a very simple example, just to illustrate the point. I have the summation, and then I have an activation function. In this case, it's called the ReLU. And so in this case, essentially, I'm summing the weighted sum of the inputs and the bias, and then I'm going to rectify with the max operator. And the output will be 1 if the summation is greater than 0, otherwise it is 0. Okay. So, by the way, for this concrete example, this is the point, the instance that I'm interested in. So I will mention this a few more times. Of course, we can also have many other machine learning models. So this is an example of a decision list. So when we talk about decision list, we are talking about ordered rules. Again, this is the instance we'll be considering. So this is the definition. So I have 4 features. The first 3 features have Boolean domain. The second feature has 3 values, 0, 1, and 2. And this is the class we can predict. This is the classification function. So what is the classification function? So again, as I said, they are ordered rules. And when I say ordered rules, it means if, else, and so on. And in this case, if x1 is 1, then I predict 0. Otherwise, if x2 is 1, I predict 1. Otherwise, if x4 is 1, I predict 0. Otherwise, if everything else fails, I predict 1. Okay? I can also have decision trees, and we'll see this example plenty of times as well. This is actually taken from a paper. Again, we have studied it a lot, this decision tree. So again, I have 5 features, all Boolean, and I can predict 0 or 1. Again, this is just for simplicity. I'm going to show that this is actually equivalent to something much more complicated. And sometimes people are interested in monotonic classifiers. So again, a concrete example that we have used is predict student grades. So again, of course, all of this is hidden, but we have 4 features: the grade in the quiz, exam, homework, and project. All the grades go from 0 to 10. And with this information, we can compute the final score, which also goes from 0 to 10, which is shown here. Okay? And then the actual grade of the student is, well, essentially it's a bunch of cases. So if S is greater than or equal to 9, the grade is A. Otherwise, it will be B. Otherwise, it will be C. Otherwise, it will be D, and so on. Just a bunch of rules again, but in this case, we can guarantee monotonicity. So what we mean by monotonicity is first we impose an order on the classes. So F is the worst, A is the best. Again, this is very intuitive. And a prediction for some point in feature space is less than or equal to some other prediction for any point that is less than or equal to the other point. Okay. So we'll see this classifier again as well. And we are interested in this concrete point where a student got 10, 10, 5, and then in the project, they decided not to do it, and they still got an A. Okay. A few more examples. So naive-Bayes classifiers are a very well-known class of classifiers. So again, here we are using probabilities, conditional probabilities as a matter of fact, and we want to predict G given R1, R2, 3, and 4. So this is how we compute the probability in a concrete point in feature space given the conditional probabilities and the evidence. Random forests again are extremely widely used as well, and in general tree ensembles, for example, boosted trees. So how does it work? Random forest, essentially you construct different trees by sampling the training data set. And then, you can also sample randomly sample the features to use. And then what you do is each tree predicts a given class, and then you pick the final class by majority voting. This is one example. There are other examples. People have also used generalizations of decision trees, decision graphs, decision diagrams. This is an example of a multi-value decision diagram. And finally, people have also used propositional languages. So this is an example of a DNNF. So you have in general, in this case, we are talking about a Boolean feature. So if you plug in the values here and you get there the prediction. So let's now, so people, you could say, but why should we care about the logic-based explainability? So let me try to motivate what are the problems with 99.99% of research on XAI, which I call non-formal XAI. So there are other approaches. I'm just going to talk the ones I feel are the most visible ones. There are model agnostic explainers and what people call intrinsic interpretability. So in terms of model agnostic explainers, very well-known examples are Lime and Sharp. So what they do is they learn a simple interpretable machine learning model, usually, for example, a linear classifier, but you could also learn a decision tree. And what you do is you approach, the approach to use for Lime, you train the classifier, you sample, and then you construct the model. Sharp is more based on game theory, so you approximate the Shapley values. Anchor is different from Lime and Sharp because you learn the features that are considered to be more relevant for the prediction. So like Lime, Anchor is also sample-based. So you sample for some time, and given that information, you predict which features are more important for the prediction. Now, I should note that these three approaches they offer no guarantees of rigor in the computed explanations, and I'm going to talk about this later. Intrinsic interpretability is different because here is the model itself that is explainable. So people have proposed this. I mentioned this already before. So people would say that decision trees or decision lists or decision sets are interpretable, so you can just use them. And the questions we asked some years ago was, can model agnostic explainers really be trusted? And is intrinsic interpretability interpretable in fact? So let me talk a little bit about this. So this is a very, very simplistic example of a boosted tree. So we have 7 classes. And for each class, we are just testing one feature. And given the value of the feature, we predict a value. And then the class is the picked class is the class for which we get the highest value. So if we consider a concrete instance, point in feature space, so this is, I believe, from training data. So
Me, I cannot hear anymore.
Okay. We lost you when you were talking about these classes.
So did you understand the, so essentially, let me go back. So essentially, this is the instance, and if we run the tool anchor on, the explainer anchor on this is what we get. So the translation is that if you have not hair, not milk, not tooth, not fins, then you should predict reptile. Yes? And let me continue. And so this would be what you get. Now, what we notice is that this same explanation incorrectly explains another instance from training data. So it's shown here, but the class is not reptile, now it is amphibian. Okay, and again, if this essentially is very problematic. So let me put it in a different way. So suppose you have a classifier for deciding bank loans. Okay, and you have two samples, Bessie, so with some values, V1, and you give the loan, you grant the loan, and you have Clive with some other values, V2, and you decline the loan. And you have some explanation, which is, in this case, we call it X, it's age 45 and salary 50K. And what from the previous slide, what we showed is that X can be consistent with Bessie, where we have an approved loan, and it can be consistent with Clive, where we have a declined loan. Okay, so essentially we have different outcomes, and we use the same explanation for those different outcomes. So again, this is extremely problematic. Okay, so you could say, well, that never happens, and what happens actually, what we discovered is that this happens a lot. So these are examples of data sets. Boosted trees, as I mentioned before. And so this is correct explanations and redundant, meaning that you have too many literals that you can get rid of. And as you can see, for example, for anchor, you can go up to 99.7% of incorrect explanations. Okay. So as I said, this is problematic. You could say, well, this is a fluke because it happens in one point of feature space, but it does not happen in other points of feature space. So what we did was we measured how often is this true, and for that we need to do model counting. So we had to go for Bayesian neural networks, different which we can encode to SAT, and then we can count. And as you can see, so this is essentially the number of examples we considered. For some examples, the actual estimate, so the number of points where you are correct can go below 50%. So you are most often incorrect. Okay. So again, this is another sign of a very problematic situation with Lime, SHAP, and Anchor as well. So let's now talk about intrinsic interpretability. And again, I would assume that everyone, almost anyone that has taken a course in machine learning would say that decision trees are interpretable. Actually, one of the creator of decision trees and also random forest wrote more than 20 years ago that on interpretability, trees rate an A star. So it is the most interpretable that you can get. So let me go back, let me look at an example that I showed before, now with more information. So this is a decision tree that was published in this paper. This is NeurIPS 2019, a few years ago. The tool is called optimal sparse decision tree. So this for this decision tree, there is the claim of optimality. So this tree is optimal in some sense, and there is some accuracy of training. Okay. And so let me continue. So to simplify the explanation, I'm going to pick the name of the features and convert them to some simple, well, MM for middle, bottom right, BR, and so on. So this is, and what we are interested in is what is the explanation for MM equals 0, TL equals 0, BR equals 1, BL equals 0, and TR equals 1. So when you have intrinsic interpretability, you give this model to your human decision maker, and you'll say, well, it is the path, of course, right? So what we are saying is, if not MM and not TL and BR and not BL and TR taken from here, then the prediction should be 1. Yes? This is, well, this is what is shown here. Well, so let me see if we can simplify things a little bit. So what we are going to do is essentially we are going to fix two features, BR and TR, and we are going to consider all possible values of the other features. And then we check what the decision tree is going to predict. And the decision tree is predicting all is 1. So essentially, this means that we don't really care about these values when these two are 1. And so the reduced explanation should be BR equals 1 and TR equals 1. Okay. And so this, notice that for a human decision maker, you start with five literals and you end up with 2 literals. Okay, so you can get a significant reduction in what you are using for explaining the prediction. So you could say, well, that's just one path, and the answer is, well, actually, there are many other paths. So here there are a total of 8 paths, 5 of which you can simplify in terms of explainability. So again, you could say, well, that was unfortunate of the authors. It happened only in that paper. So let me show that it can happen a lot. One way is this. So if you have a classifier, this is the function that you are predicting. And so you can construct a decision tree for this function as follows. So you pick, actually, you can pick the order. So you pick the order I1, it can be any value from 1 to M and so on. So you first test I1. So if it's 1, of course, you predict 1, otherwise you don't know. You go for I2. If it's 1, it's 1, otherwise you don't know, and so on, until the final feature. If it's still 0, you don't, it's, in this case, since all are 0, it's 0, otherwise it is 1. And so next we ask the question, for this concrete point where you have 0, 0, 0, 0, 0, and then 1, clearly the prediction, it's going to be this path here, the prediction is 1. So the explanation using the decision tree would be that if the first one is 0, the second is 0, and so on until the last before the last is 0, and the last one is 1, then you predict 1. But it is clear, given the function, that it is enough that as long as the last feature is 1, you're going to predict 1. Okay. So the point is that the actual explanations can be arbitrarily smaller than the paths in the decision tree. And so we have been claiming now for 2 years that decision trees should not be deemed interpretable. And of course, this is true as long as you equate interpretability with succinctness. So if you want succinctness, as I just showed, well, you cannot use paths in decision trees. You could say, again, this is a concocted example. So what we did is we went through the books, machine learning books and AI books published over the last, well, many years, since the 80s, I think. And what we did is we picked examples of decision trees in these books. So it's shown here which chapter and which figure. And I'm just going to highlight 2 numbers. So the percentage of paths which we can reduce, so we can find a smaller explanation. So as you can see, it can go up to 60%, 50%, 50%, 80%, and so on. And then, of course, you could say, well, the path itself is redundant, but the number of features that are redundant is very small. And so this means it's the average number of literals in the tree that are redundant. As you can see, in many cases, you can go up to 50%. Okay, so you can essentially get rid of 50% of the literals in those examples. And as I said, these are published examples in books that goes back 4 decades. Sorry. Okay. So just a few examples that everybody should be familiar with. So this is the decision tree shown in Russell and Norvik's book. And so let me go here. So for example, if it's full, yes, tie, and no, so notice that it is clear that the prediction is going to be no if instead of being angry, you are not hungry. So it's clear redundant, and you can in this case, the explanation could be simpler than what the decision tree is saying to you. This one is taken from Zhu's book. So again, you can see there is a pattern here. So you can look at this, but essentially by looking at it, it's clear that if the prediction is crossed, then you don't care about why. Another example, very similar example from Alpaiden's book. So here, if the prediction is a circle, then you don't care about X1. Shalef Schwartz and Ben Davies' book. Again, if the prediction is not tasty here, then you don't care about color. And this is, I showed already this example before. This is from Poole and McWhorter's recent book. So here you have lots of examples. So as you can see, so for example, suppose you are here, so you have this path here. So you predict reads. So if you are predicting reads, clearly you don't care about thread. And if you are predicting here skips, then you don't care about length. Okay, so lots of examples. Now you could say, well, this is because people create small examples for teaching purposes. In real life, that doesn't happen. So what we did is we created decision trees from data sets using two different tools. ITI has been around for almost 2 decades, so it's pretty old. IAI is Interpretable AI. This is a company in the US that is creating the optimal decision trees. And this is a bunch of data sets. And as you can see, we are using the same characteristics. So the percentage of redundant pads can go up to 86%, 80% of the pads. And the same here in this 87, 50, 80, and so on. And for the pads that are redundant, the percentage of redundant literals can also be very, very significant. Again, as I said, this is ubiquitous in decision trees, so it happens all the time. So arguing that you can use decision trees for interpretability is really a misconception. So, so having said all of this, let me just briefly deconstruct a misconception that exists a lot, that you cannot use logic for machine learning models. So let me start simple and then complicate things. So let me look at suppose you have these two features. This is your set of rules, unordered rules, yes? And suppose that you want just to understand the model, you ask the question, can the model predict both plus and minus for some instance? Of course, this is not interesting, but if it happens, we should know, right? And of course, if you look at this, it might not be easy to understand, but you can essentially, well, if you think about it for a while, it becomes clear that if you pick one here, sorry, if you pick 0 and then you pick 1, it's clear that you are going to predict both. And so how can we find this automatically? Well, we can essentially create propositional variables, yp for the first statement and yn for the second statement, and we want both of them to be true. So of course, since we have linear inequalities, we need an MILP solver or an SMT solver. But essentially, we want to find a model such that this is true. Okay, so it's just an example. Let me show you another example. Another set of rules again, and we ask the same. Can we predict both plus and minus for some instance? This looks more complicated. So what we do, because we have two types of, we can predict minus in two different ways. Again, this is not very, well, we can predict plus and minus at the same time. And the formalization is very similar. So we can predict pluses, we can predict minus, and we predict a plus in this case in only one way. Minus we can predict in two different ways, and that's it. Okay? And so in this case, because we don't have linear inequality, we can just use a SAT solver, and a solution essentially shows that there are points in feature space where we have what we call overlap, so we can predict plus and minus. Now, of course, some people will say, yes, but we want to do neural networks. So let's do neural networks. So suppose, again, it's a very simplistic model to fit on the slide, of course, but the ideas apply in general. So each layer, okay, we call this a block. The first one is just inputs, okay? And so what the blue boxes are doing, they compute an intermediate value, x prime, given the input and the weight matrix and some bias vector. And then they compute the output given x and some activation function. And we are going to use, as I mentioned before, ReLU for the activation function. Okay, so the question is, how do you represent this in such a way that we can reason about it? And so what I said in the previous slide is that x prime is the weight matrix dot product, the inputs plus some bias vector, and then we take the max for the ReLU operation. And there is, of course, there is an encoding. So what we do is we are going to use two positive variables, yi and si. And the idea is as follows. If this summation is positive, well, we are going to put it in yi, which is what we want. It's the max. And if the summation is negative, then we are going to put it in si, which is positive. And so minus the positive is negative, of course. And we are going to put yi with value 0. How can we instrument this? Well, we have another Boolean variable, which essentially forces either yi or si to be 0, because they are both, well, they are positive, and we are forcing one of them to be 0. And the other one takes the value from the summation. Okay, so essentially we can view si as the slack variable that keeps the value that we don't have a place to put besides itself. Okay, there are simpler encodings, but not as effective for reasoning about this. And so the one thing I would like to convey to everyone is that modeling machine learning models with logic is possible, of course, and usually not very difficult. So then this is, as I said, a misconception that some people have. Just the example I showed at the beginning of the course. So for this example, this is the MILP encoding. So we do the summation here. And then we say that it's y1 minus s1. So again, if it's positive, it's y1. If it's negative, it's going to be in minus s1. And then z1 essentially picks which one we are going to have non-zero, either y1 or s1. And then finally, we pick y1 is the Boolean variable. So if y1 is positive, we predict 1, otherwise we predict 0. And so these are two examples where we plug in concrete examples and we see what happens in terms of the neural net. Okay. So are there any questions for part 1? Okay. If not, let me talk a little now about formal explainability. So our take for the last 3 years on explainability. So I will talk about objective explanations first, and contrastive explanations, and then talk about a few more results and case studies. So as I said, we are here for objective explanations. We are going to answer a why question. So why the prediction? And we consider, as I said also at the beginning of the talk, a concrete instance VC, such that C is the prediction of a given V. So an objective explanation, we call it AXP. Some other authors have called it PI explanation. Is a subset minimal set of features, so a subset of the features that is sufficient for ensuring the prediction. So what we are saying is that if we fix the features in this set X for any point in feature space, if they are fixed, then the prediction is going to be C. Okay. And this is just, so notice that this does not require the set to be minimal, so we call this a weak AXP, because we are not requiring X to be minimal. The definition of AXP is that, well, it has to be a weak AXP, and then any proper subset must not be a weak AXP as well. Okay? And so, if you look at this predicate, you'll see that it is monotone on X. And so this means that instead of having, notice several things. So the definition here is complicated because we must look at all proper subsets, and they can be an exponentially large number of proper subsets. So what we do is that we look at this definition, we see it is monotone, and this allows us to simplify this definition by saying that it is enough to look at removing just one element and requiring that it should not be X minus that element should not be a weak AXP. Why? Because if this is the case, then for any proper subset, it will also be the case of monotonicity. Okay, and so this is what in practice people use to compute objective explanations. So how do we find one AXP? Well, we start with all the features. And then if we start with all the features, it's certainly going to be an AXP. Why? Because if we fix all the features, certainly the prediction is going to be what we started from. And then we are going to analyze features in any order. You pick the order, one feature at a time. And if we drop the feature and it's still a weak AXP, this means we don't need the feature for being for explaining the prediction. Then we can remove the feature from the set. Okay. So let's see a concrete example. We saw this function before. So what we are going to do is we are going to look at a point 0, 0, 0, 1 with prediction 1, and we want to compute an AXP in this case. So the set of features is 1, 2, 3, 4, the initial set of features. And essentially what we do is, can feature 1 be removed? Notice that this is the definition of weak AXP. And so what we are going to do is, if feature 1 can be removed, then we are going to essentially here we are going to drop from x1. So we have not x2, not x3 and x4. So because of the point in feature space, and we want to know if this implies that the prediction is going to be 1. And of course, because x4 is 1, clearly the prediction is going to be 1. So yes, so we can essentially remove x1. Feature 1, sorry, we can remove feature 2 for the same type of reasoning. Notice that here we already got rid of feature 1 and we can get rid of feature 2. Why? Again, because since x4 is 1, we get the prediction. And of course, this means that For feature 3 can also remove it for the same type of analysis. So X4 still guarantees that the prediction is going to be 1. And now we can ask the final question, can feature 4 be removed? And the answer is, well, no, because it's the classifier is not always true. So if we allow X4 to take any value, this is not guaranteed to be 1. So the answer is no. And so this is my objective explanation. In this case is 4. So as long as feature 4 takes value 1, the other features can take any value that the prediction is still going to be 1. So of course, here I asked you and me to do this analysis by hand. Usually what we do is this type of validity and consistency will be checked with a type of one automated reasoner, and I'll show you a few more examples of this. What we also noticed is that for some classes of classifiers, there are polynomial time algorithms, and I'll mention this later in the course.
There is a question here on the.
Yes. So let me go back. Yes.
It says from Brede, is this a local explanation for a prediction or a general explanation of the classifier?
Yeah, that is a very good question, because I think there is a lot of confusion there. So this is a local explanation. It's localized because we are focusing on this point in feature space. What we are ensuring is that we have global guarantees in terms of the explanation. Okay? So the explanation holds true in all points of feature space, but we compute it locally with respect to a point in feature space. Okay. So contrastive explanations. We start from an instance as well, and the contrastive explanation is a subset of features which, if we allow them to change value, this is sufficient for changing the prediction. So what we are saying is that there is a point in feature space. If we fix the features that we are not allowing to change, but we allow these features to change, then we can change the prediction. And again, we can use the same type of approach that we did before. We can define a contrastive explanation, so a subset minimal, by being weak CXP, and then any proper subset must not be a weak CXP. The definition is again monotone on the sets, and so we can simplify the definition of contrastive explanation by just looking at the set minus one of any of its elements. So it's much easier to do. And the same algorithm can be used. It's exactly the same algorithm where we just use a different predicate that we did before. So let me illustrate this. So again, we have the same classifier, the same instance, so the same point in feature space, and we start from the same set of features. And notice that now the condition is different. So we require equality for the elements that are not in the set. So since we start here with all the elements, there is nothing here. But now we are asking X1 to be removed, so X1 is no longer in Y, so it appears here. So can we change the prediction? Can we change still the prediction if we fix X1 to be 0? And the answer is, well, yes, because we just need to change X4. So the answer is yes. And we continue. So can we, if we remove feature 2, now it appears here, since we are now fixing it, can we still change the prediction? The answer is yes, because we just need to change 4, and we do the same for 3, and yes. And if we try to now to remove 4, this means we are fixing all the features. Then the answer is no. So again, in this case, the contrastive explanation is just 4. Okay. Any questions? Okay. So a few more results about this. So what we proved is that objective explanations are minimal eating sets of contrastive explanations, and the argument goes back to the results of Wright and in model-based diagnosis. Okay, and so this is very important because we can compute objective explanations from contrastive explanations and vice versa. Another point that people sometimes miss is that objective and explanations and contrastive explanations are model-based. So explanations will be sound given the model. So we completely trust the model. And this is very different from other approaches that essentially what they trust is the data set. And our explanations, going back to the question, our explanations are localized explanations. So they are computed with respect to the point in feature space, but they hold globally because we use universal quantification. And so there is a different type of, going back again to the question, we could consider global objective explanation. So instead of looking at a point in feature space, we just care about the class. And what we proved a few years ago is that we can define counterexamples. So this break the prediction of the class. And then we show there is also duality between global explanations and these counterexamples. And besides this, we show there is a connection, a tight connection with adversarial examples as well. Okay, so let's go back to the decision tree again. Why the decision tree? Because it's easier to look at. Okay, and so this is the decision tree I showed before several times. Again, this comes from that paper, NeurIPS 19 paper. And what we do here is to explain the explanation, to justify the explanations. We show part of the truth table. So here we fix x3 and x5, and we allow all the others to change value. Okay, and so why are we doing this? Because if we look at this part, essentially we are saying that as long as x3 and x5 are fixed at 1, the others can take any value that the prediction will be 1. And so this essentially is my abductive, this is a weak abductive explanation. And what we can see is that if we drop one of the other, one of x3 or x5, then we can the prediction can change. So we need both. And this means they are subset minimal. For contrastive explanations, we do something similar. So what we do is here, we came here and we fix these guys. And we look at these guys here and see how many do we need to change a prediction. So notice that if we just change x3 to 0, we change the prediction immediately. So this is one example of a CXP. And similarly, if we change x5 to 0, then we can change a prediction to 0. So 5 is also an example of a CXP. Now, this is one way to do it. Another way to do it is just say, well, since this is my XP and there are no others, then by hitting set duality, 3 and 5 will be the CXPs. Okay. So so again, I hope this is clear. Let me go back to a very different example, which I also showed at the beginning of the course, a decision list. So ordered rules, and this is the complete truth table. So the values and which rule fires and what is the prediction. And so so let's concrete, as I mentioned also at the beginning of the course, so this is the instance we are interested in, 0012. So 0012, this is where we are. So the prediction is 1, and the rule that fires is the default rule. And now the question is, okay, what is the explanation? And so it's easy to see that 1, 4, 1 and 4 are sufficient, because if they are 0 and 2, 0 and 2, 0 and 2, and 0 and 2, the prediction is always 1. Okay. So this is my abductive explanation. And again, the CXP is well. If we look at again the point where we are in feature space, and if we allow one to change, for example, if we go from here to now, so it becomes 1012, 1012. Here we change the prediction. So yes, and the same for 4. So we show that 1 and 4 are contrastive explanations. Again, we could obtain them by hitting set duality, as I said before. Okay. Very good. Any questions for part 2? Okay, so I see there is a question. You can ask or just type. I cannot hear anything. I presume you are still hearing me.
We are hearing you, João.
Yes. So it doesn't really. The question is, okay, have we done numerical features for decision trees? And the answer, it doesn't. Yes. So let me go back. It doesn't matter. Actually, it doesn't matter, because notice that I forgot to mention that. Of course, there is a lot of information in the slides. So notice that here we are not using equality. We are using set membership tests. So if you want to put real values, fine, not a problem. Of course, you could say, and how does that impact the ability to compute explanations? I'll talk about that when later on, but the answer is yes, it can be done. I will talk about this a little bit. So yeah, so the same person is asking if the effort is harder. Well, no, it's not. Actually, it's not. And if you give me well, half an hour, 45 minutes, I will explain why not. So it's not really a problem. Not in the case of decision trees, at least. So again, if you want to, again, I don't want to go ahead, but just to say that as long as we have univariate features, so decision tree, so each node just tests one feature, then we can do explanations very efficiently in decision trees, even if they are real value. Okay. So are there more questions for part 2? If not, let me, well, until now I've defined things, but I argued with truth tables how you get explanations. What I'm going to do now is show you how we can compute them. So how do we compute explanations? So let me give you, so notice that, let's start with the definition. So this is what the definitions we use for weak AXP and weak CXP. Again, this comes from previous slides. And this is, of course, this one is easier to analyze. This one looks complicated because we have the universal quantifier. So what we do is, there is someone that should, I'm hearing some sounds. Okay, so what we can do is we can encode predicates as follows. So for AXPs, we double negate. So essentially what we say is that we don't want, and then we introduce this call, a consistency check on the logic representation of this statement. Again, what is the logic representation? It depends on the theory that you are going to use. So it depends, and I'm going to show you some examples as well. And so for AXPs, the predicate is you don't want consistency, and for CXPs, the predicate is that you want consistency. Notice that what is inside is exactly the same with the exception of the sets. Okay. So now what do you want to do? Well, we can do subset minimal or cardinality minimal sets. So how do we do this? Well, this is essentially the algorithm I mentioned before. Let me just go through it because I think it has been around for many, many years in different areas. So you start with the complete set. And for sure you have this invariant, so the predicate holds for the initial set. And then you go through the features, and again, the order is irrelevant. Well, when I say it's irrelevant, it does not change correctness. It will change the AXP that you're going to compute. And if you drop the feature from the set S and the predicate still holds, that means you don't need the feature for the prediction, so you drop it. Okay. And so notice that this is completely abstract, so we can use this procedure for abductive and for contrastive explanations as well. What changes is the definition where you start from of the set. Now, this is a very simple algorithm. I'm going to show you a more complicated algorithm. Now, this is to compute the smallest explanation. So sometimes you might be interested in not finding one explanation, but the smallest possible explanation. And so it's easy to prove that in most cases you have a bump in the complexity class. So in most cases it will go, if it's NP complete, NP hard, you go to sigma to P hard to compute the smallest explanation. And so the approach is, we call it fitting set dualization. So we are going to keep a set of fitting sets of things we have already computed. And then at each step, we find a minimum hitting set, minimum weight or minimum cost hitting set of this set of sets. And if the predicate holds, then since it's a minimum possible hitting set, then we have and the property holds, we cannot find the smallest set. So we return it as the smallest possible AXP. Otherwise, we need to block what we started from, so this minimum hitting set, and then block the set such that it is not repeated and repeat the process. So of course you can, so this might look simple, but it's not, because you can execute this while loop an exponentially large number of times in the worst case. And each time you are solving a minimum hitting set problem, which is NP hard as well. So there is a lot of hidden complexity in this approach. And this shows, and I'm going to talk a little bit about that. This is for AXPs. For CXPs, it's actually much easier because essentially it boils down to solving maxat. So if you can solve maxat, and there are lots of tools for that, then you can compute the smallest explanation. And when I say maxat, is for if you can encode to propositional logic. If you cannot, you can use max SMT, for example, or mixed integer linear programming. So let me show you what has happened in the last 3 years in terms of computing explanations. So This is the first results from 2019 for neural networks. I'm going to talk a little bit about the size of the neural networks. And so in this case, we have a bunch of data sets. This is the number of features. And what we computed was subset minimal explanations and smallest explanations as well. And as I said, the complexity of computing a smallest explanation shows, for example, here. So it takes much more time, or we cannot compute at all the smallest explanation. We used SMT solvers and mixed integer linear programming solvers. And you could say, but how did you do that? Well, I showed you the encoding of neural networks at the beginning of the course. And so this was the first rigorous, absolutely rigorous approach for explaining neural networks. So these are positive news. The negative news is that we can do this for a few tens of neurons. So this was in 2019. Okay. Since then, we have been putting effort trying to understand what can we do. And this shows what we have achieved since 2019. So I call this the efficacy map. So we have two dimensions. Here it's what we know about computational complexity of the problem. And here is how effective in practice our algorithms are. So green, the classifiers marked in green means we can compute one explanation in polynomial time, and it's shown here, and they are very effective in practice. So the algorithms run very efficiently. In blue, we have other classifiers which we have proved that they are computationally hard to explain. But the logic encodings that we have devised are very efficient in practice. And I'm going to show you some results about that. Now, these are the good news. There are still some bad news for Bayesian network classifiers and for neural networks. So we know that they are computationally hard or very hard, and they are very ineffective in practice. So these are still the bad news that we have. Now, this is a summary. Let me just show you, for example, naive Bayes classifiers, monotonic classifiers, decision trees, decision graphs and decision diagrams, different propositional languages, decision lists, random forests, boosted trees. All of this we can explain very, very efficiently. As I said, we don't explain all the classifiers that exist, but many classifiers we can explain very efficiently. Let me show you some results to convince you of that. So this is a bunch of data sets. Here we use random forest, SAT oracles. So we show that in the case of random forest, we can use SAT oracles. This is the size of the random forest. So notice that the depth is reasonable, or again, goes from 4 to 8, which is pretty significant for the decision tree. And then we have, I think, 100 decision trees. So this means that the number of nodes in the decision tree can be in the random forest can be quite significant. And this is the times it took us to compute explanations, the average, and this is the average time. So notice that it's on average to compute one explanation, it's less than a second with a few exceptions. This is interesting because it's quite efficient, and these are fairly large random forests. It is interesting, but what is more interesting is that we compared with Anchor, and notice that Anchor is not computing a rigorous explanation. And we are almost without exception, or in most cases, the vast majority of cases, we are faster than Anchor in computing a rigorous explanation for a random forest. So I think this is pretty significant. Okay, very good. So are there questions for part 3?
I have a question, João. I wasn't clear. Are you looking for abductive explanations here or contrastive explanations? You mentioned that there might be a difference in complexity.
Yes, well, there is a difference in complexity for computing a smallest. Here we are computing subset minimal, and so it's the same approach, the same complexity. Well, the complexity is different, but the type of oracle that we use is the same. Okay, so essentially we can use a SAT oracle to compute a subset minimal. We don't use one SAT call. We use a linear number of calls to a SAT oracle. So if the number of features is, for example, 64, this means in the worst case, we are going to make 64 calls to a SAT oracle, and so on. Okay. Any other questions? Right. So essentially, in this case, as I said, we are using SAT oracles. We have for boosted trees, for example, because we are going to compute summations, we have used SMT, Max-SMT oracles. So it depends a lot on the type of, as I said, it depends on the logic that you use to represent or to encode the classifier. So here we were very lucky because we found a way to use SAT oracles, and so, well, they tend to be more efficient. In some of our papers, we have done boosted trees, and in those cases, we are using SMT solvers, for example, or Max-SMT. Okay. Any other question? Okay, so let me. Well, I can. I would put the break here because well, that's what I was planning for, and unless you prefer me to continue, if for some reason. If for some reason you cannot hear me, just let me know. Also, please do ask questions, and if there is something that is not clear, just again, please do ask. I would start going back to the previous part so that I can recapitulate a little bit. So what I did in the previous, just at the end of before the break, was to introduce these predicates for computing one AXP and one CXP, and then showed you generic algorithms that can be used with, well, in this case with both, and in this case with AXPs. Why just with AXPs? Because it's easier to compute CXPs when we are computing the smallest. And then I talked about progress and what we had achieved until now. And I showed you some results, some good, some not so good, and some much better results. And so if you don't have questions, I will proceed from here. Okay, so let's now talk just a little bit about encoding. So because you could ask, okay, how you showed the predicates, but how is this done? And what I'm going to do is illustrate just one case. So let's look at the decision lists, which I mentioned during the first part of the course. So in the general case, we have a bunch of so decision list is a set of ordered rules shown here. So we have a bunch, one body, another body, and so on for each rule. And so if this body is true, then we predict the one. Otherwise, if this one is not true and this one is true, then the two, and so on. And so the question is, how do we go from here to computing exponentials? Okay. And what we actually, if you go through the papers and through the notes, there are different ways of doing this. This is just an illustration how you can attack this type of problem. So what we do here is as follows. So what do we need to represent? So in general, if we have some formula and what I'm going to describe is a propositional encoding. So if you have a formula, a phi, we represent the propositional encoding with like this. So it is a set of clauses with a bunch of variables. We don't care about most of the variables. We just care about one variable, which is one if and only if the formula takes value 1. Okay. Of course, these ones will be used, but not for talking about the encoding itself. So what do we need to encode here? Well, notice that we have two components. So we have the different terms, and we need to be able to encode them. And so we are going to encode the term tau j with some set of clauses and a bunch of propositional variables, one of which will be tj with this definition. And if you recall the definition of abductive or contrastive exponential, we also ask for equality of the value of a feature and a given point in feature space. So we also need to encode equality. Notice that you could say, but why do I care about this? Well, because the variables need not be propositional. They could be integer valid, real valid, and so on. So we need to be able to encode that. Again, we have a bunch of clauses to do this encoding, and such that Li is true if and only if I have equality. And finally, notice that we are always looking at an instance that predicts class C. Some of these Ds will be class C, some of these Ds will not be class C. And so I'm going to use a propositional variable just to represent the case where DJ matches C. So it's one if and only if I'm matching C, otherwise it's not. Okay. And so what I'm interested in is I want to look at all the bodies of all these rules, and I want to know which rule is going to fire. So TJ fires here, for example, it must be the case for this one to fire, the other ones did not fire. But in general, I'm only interested in the, notice that, again, I'm assuming that TJ is different from C, because again, I'm trying to get a different prediction from C. So I care about the cases where before J, I would get C. So in these cases, so notice that this would mean EJ equals 1. In these cases, I cannot have, I would want TK for K less than J to be inconsistent. So I fire J if TJ is true, so it's from this encoding, and for the values of K less than J, such that the prediction would be C, I don't want it to fire, because if it fires, the prediction would not change, would be C. Okay, so this is part of the encoding, of course, just the first part. This is, so essentially, if rule J fires, I'm going to change the prediction. Again, I'm assuming DJ, as I said, is different from C. How do I do this? How do I ensure that I change the prediction? Well, I go over all the rules which have a prediction different from C, and I ask that one of them should fire. Okay. So essentially, this is the bulk of the encoding. Of course, there is a lot of fitting detail, but essentially, what do I have now? Well, what I have now is I start with a set of soft clauses, the allies. If you recall, let me go back. I need to go back in this case. Well, it's here anyway. So the ally is associated with the equality literal. So essentially, what I'm saying is that the additional knowledge is that I have equality in all cases. And then I have the hard clauses are the representation of the equality, the representation of the terms, the fact that I want, if I know how to file rule J for any J, and I want one of the J's to file when it's different from C. So this represents the condition for changing the prediction. Okay, and of course I'm sure that if I fix all the literals, well, then this is going to be inconsistent because this is requiring the prediction to change, and this is forcing the prediction to be C. So why am I saying this? Because now I have essentially I go back to where I started. I have a background knowledge such that with additional knowledge it is inconsistent, and I want to find a subset minimal set of variables, of literals, such that it is still inconsistent. So that's an MUS, and that means that would be also an AXP. And so we can equate MUSs with AXPs and vice versa, and MCSs with CXPs and vice versa. And so this allows me to find, so I can use technology that has been around for more than a decade to use here to compute explanations. I hope this was clear. So essentially, I just have to plug in. Of course, I did not say how I do this encoding and this encoding. That depends a lot on the terms I'm using. So if I'm using Boolean variables, it's very easy. If I'm using integer values, it's a bit more complicated and so on. And in the notes, I show an example. So of course, just to illustrate several things about this plot. First, you could say, what is enumeration? Well, I'll talk about this later. The point is that so these are different data sets, and why did I? So enumeration means I go through all the explanations, and the point is that the tool is so fast to compute explanations for decision lists that so this is seconds. So only in a few cases to go through all the explanations it takes more than 10 seconds. Okay, so in most cases it is instantaneous to compute all. So computing one will be very, very efficient. That's why I'm not showing it. It's so efficient. I prefer not to show it. I show you aggregated numbers. Okay. Any questions about this part?
Some tiny details I probably missed. So we are talking about the soft constraint. So what is the intuition between soft constraints here?
Yes.
What are these
Very good.
RIs?
Yes, very good. So that's a very good question. I mentioned this in passing. So as I said, B is the background knowledge, as S is the additional knowledge. We call them soft clauses because they need not be satisfied. Okay, and the goal usually is I want to find a subset maximal or maximum such that they are I still respect these conditions. So In this case, if I put all these clauses in this, I'm going to get inconsistency. So I'm interested in finding either a subset maximal or a subset minimal. In this concrete case, it's subset minimal, set such that this condition is still true.
Mm-hmm.
So I don't, the point is that I'm not interested in all of the soft clauses. I'm interested in a subset of the soft clauses such that, so I pick a subset of S such that if I replace S by that subset, this is still true. And if this is still true, this means that I'm still not predicting a class different from C, I'm predicting a class that is C. Okay?
Mm-hmm.
So that's the trick. Again, this depends, of course, on the type of classifier. I'm showing for a concrete classifier. For other classifiers, we use different modeling approaches. Okay?
Yep. Thank you.
Okay, so let's now talk about tractable explanations. And with this, I will try to answer some questions I got in the first part of the course. So let's talk about decision trees. So of course, I could use what I just described for explaining decision trees. Why? Because you can view a decision tree as a decision list. Okay, so it's if else, and so on. Okay, so you could do that, but of course, so let's look at this example, which we have seen already several times. So as I said, we could use the approach I described in the previous slides, and so run an algorithm to compute adaptive explanations or PI explanations the same, using NP Oracle. This would be worst case exponential, but it would certainly be possible. But in this case, we can do better than that. So suppose if you recall, I'm interested in this path and in prediction 1. So if I want the prediction to be 1, what I just need is to ensure that all the paths that have prediction 0, that they remain inconsistent. So I cannot find a way to get to 0. Okay? So that is the intuitive representation. So essentially what I need to do is find the subset minimalistic set of all the paths that have prediction 0. And these subset minimalistic set are the features that I have to keep, because if I keep them, well, then I'm going to guarantee that I still predict 1. So in this concrete case, notice that to get here, I need to hit this one. I don't have another option. To get here, I need to hit this one, and to get here, I need to hit this one or this one. So a minimal hitting set would be this one and this one. Now, this is known to be solvable in polynomial time for many years, and so we can just use an off-the-shelf algorithm. Okay. So in the notes, I describe that we can also use a Horn encoding. That's an alternative, and it's usually quite efficient as well. Okay. So let me repeat. So here, what is the idea? The idea is that I'm predicting 1. And if I will continue predicting 1, as long as I cannot find a way to get here, or here, or here. How do I do that? Well, I must ensure that I cannot get here. So the only way is to block here. Here is the same.
Just some details I want to understand. When you talk about polynomial time, is polynomial with respect to the size of this tree, or is with respect to the number of the conditions here?
Well, it's a polynomial with the size of the tree. Why? Because essentially we need to traverse the tree, and so we need to write down the conditions to block the paths to prediction. In this case, prediction 0. So I notice that. So if I want to make sure that I don't get here, so if I allow this to change, well, then I will be able to get here. If I don't want to get here, I need to block this one. Okay. Here is the same. If I don't want to get here, I need to block this one. So this cannot change. Notice that if I allow this to change, this means I could go here or here, so it's not interesting. And if I allow this to change, I could go here or here, but it's not interesting because I still can go here. So the only way to block access to this 0 is to block it here. And here I have 2 options. So again, if I can go here, so that's this is inconsistent. So if I fix this one, I will continue going that way, so I will not come here. And the other option, this is not interesting because it's there as well. So this one is interesting, this one is interesting. So I need to block, so this is, if you recall, I need to fix block bottom right or bottom right, top right, and top left and top right. So the only solution is to block, to fix bottom right and top right. I don't have any other solution. That's the objective explanation I showed before. Okay. So so this is what I showed before. Again, we have, as I said, there is a lot of redundancy in decision trees that are produced even by very modern tools, commercial tools. And the percentage of pads that exhibit objective explanations can be very large. And the number of literals that we can drop can be quite significant. So 40%, 45%. Of course, there are smaller cases, but these are the ones we should be concerned about. Okay. Any more questions? So let's change gears a little bit and talk about monotonic classification, just to illustrate the range of tools that we are using. So if again, so how do we? What is the idea? The idea is that in monotonic classification, we are going to assume that features can, well, they are ordered, so they can go from a lower bound to an upper bound, each feature. Okay. And the idea is that we are going to refine lower and upper bounds on the prediction. So we are going to keep a lower bound on the prediction and an upper bound on the prediction. Okay. And so we need to be able to play with the different features. So we need to be able to fix a feature and to free a feature. So how do we fix a feature? Essentially, well, we have a set that we are going so we are going to fix the feature. It's going to move to a different set, and we are going to fix it with the value we started from. So that's how we fix a feature. And to free a feature, essentially, we are going to allow the feature to take any value. And again, we are assuming that it will move from one set to some other set. Okay. So that's, we are going to use this as utilities for the algorithm. And so this is how we compute. So the idea is that we start with the lower bound and the upper bound with the pointing feature space V. So for sure, the prediction will be the class C, and here the class will be the class C. So this is guaranteed. And I'm not going to talk about 4 and 5. This is just a seed initialization. If we can start, if we want some seed, I'm not going to talk about this. I'm going to talk about this part. So the idea here is as follows. Again, assuming that S is the empty set. So I'm going to look at all the features. And what I'm going to do at each step is I'm going to free one feature. And I'm going to see if the prediction changes. If the prediction changes, I must fix it. It cannot be free. If the prediction does not change, then it can be free. So I will let it free. Okay. Notice that this algorithm in lines 6 to 9 is very similar to what I showed before, in this concrete case adapted to monotonic classification. So let me show you a concrete example. This is the example I showed at the beginning of the course today. So we have that the lower bound is 0, if you recall. That's all the grades, and the upper bound is 10 for all the grades. And the point was, if you recall, 10, 10, 5, 0. 0 is the project and so on. And the grade that the student was going to get was A. So what I'm going to show you is the rationale for computing 1AXP. So we start, so these are the features, but when we start, notice that the lower bound and the upper bound are 10, 10, 10, 5, 0, 10, 10, 5, 0. And so this means that the prediction is A, because again, this is exactly what we get in this point. Okay. So in this case, what we are going to do now is drop feature 1. And so this is going to change the lower bound and the upper bound, the representation of the lower bound and the upper bound. And so the prediction now for the lower bound is C, and the prediction for the upper bound is still A. Okay. And so here I must keep the feature because I'm changing. So now I can change the prediction. So I need to keep the feature. So I keep the feature, 1 is kept. And so the lower bound and the upper bound will be the same again. Okay. So now I move to feature 2. Notice that this is what I have there. So the same. And now if I make the feature 2 free, this is now the lower bound and this is the upper bound. And if I compute the prediction for in this case and in this case, I go from E to A. So again, because I'm changing the prediction, I need to keep feature 2 as well. So I go back to the original situation. Okay. And now for feature 3, so again, notice that this is what I'm going to get here. Now for feature 3, this is now the lower bound and the upper bound. So what is the difference? Essentially, what I'm going to do here is I can go from 5 to, I can go now, I can have 0 here. And so this is what I get. Now I don't change the prediction. So I have, in any case, I have A. And so I don't need the feature 3. So this is now the new upper bound, a lower and upper bound. So I don't notice that at this point I dropped feature 3. I go to 4 and notice that this now reflects the new lower and upper bound. There is a difference here. And now if I have the lower and upper bound, if I've changed the feature 4, notice that I essentially on the left I don't change anything, but on the right I change because I'm allowing the fourth feature to take any value. So I go from A to A. So this means feature 4 is not relevant, so I can drop it. So the point is that, sorry. So essentially what I'm saying is that the XP will be 1 and 2. Okay. Notice that the rationale is very similar, but we are now we adapted the algorithm to talk about, well, a monotonic classification and well, discrete or continuous valued features in this case. Okay. Any questions about either the decision trees or monotonic classifiers?
I have one about the decision trees. So you mentioned there this horn encoding.
Yes.
So I was wondering if there are any properties that you can give such that then you know that the encoding is horn, because this seems to give polynomial algorithm, right?
Yes, it does. But notice that's what I said. We already have a polynomial time algorithm. That's what we claim here. And if we do a Horn encoding to compute a subset minimal set of features, so an AXP or a CXP, the Horn encoding will run in polynomial time. To solve max-out, of course, it is NP hard, but to find a subset minimal set, you can do it in polynomial time. So the idea essentially is that you are trying to capture the conditions. So you are trying to ensure that this guy is blocked, so you cannot get here, you cannot get here, and you cannot get here. So this is your background knowledge, and then the soft clauses will be that you would like, of course, all the features to be free, and that's your Horn encoding, and then you just give it to a Horn reasoner that can handle, of course, soft constraints as well. Okay.
All right. Thanks.
So very good. So this is okay. So now so essentially what as I showed at the beginning, the timeline. So I said what I'm doing is covering the timeline. I started with defining explanations. Then how can we compute explanations? How can we compute explanations when we have tractability? And now I'm going to talk about a few some problems that are a bit more challenging. So I'm going to talk about two topics, well, three, more than two, but two in more detail. Enumeration of explanations, number one, and feature membership, number two. So of course I will explain what this means. So the big question for enumeration is, how do you navigate the space of explanations? You could say, why is this interesting? Well, suppose you give an explanation to a human decision maker and he's very unhappy with the explanation. How do you find another explanation, a different one? Right? And so this is what the goal of enumeration is, to iteratively go through the explanations that are not yet listed. So there are some complexity results. We proved 2 years ago that for naive-based classifiers, we can enumerate the explanations with polynomial delay, and this is pretty good. It was a very nice result. For monotonic classifiers, we have also proved that enumeration is computationally hard. So we should not expect to be able to enumerate efficiently. And for decision trees, we proved that enumeration of contrastive explanation is in P. And again, this is also, well, interesting. I will talk more about some of these results. As I said, there are algorithms for enumerating contrastive explanations. So we could just enumerate MCSs, and this has been around for many, many years. There are no known algorithms for direct enumeration of abductive explanations. So this is different here. So enumeration of CXPs, you can enumerate them directly, like enumerating MCSs. But in direct enumeration of XPs is like enumerating MUSs. There is no direct algorithm for that. So essentially, there are two ways to do this. You can enumerate all the MCSs, all the CXPs, and then use dualization. But this is often not realistic. Okay, this why? And the idea is that if you have to start with enumerating all the CXPs, and you could have an exponentially large number of CXPs, so you might never terminate enumerating the CXPs before you start enumerating the abductive exponentials. So the best solution is what we call the Markov-like algorithm, and this has been around for a few years for enumerating MUSs. So essentially, the idea is that you enumerate abductive exponentials and contrastive exponentials on demand. And so let me see what I have. So essentially, this is how the algorithm works. And notice that this shares some similarity with the in terms of organization with the algorithm for finding a smallest exponential. So the idea is that you have to find a way to block previous exponentials. So you have this set H, and then you are finding solutions on this set H, SAT solution. So essentially, what you are going to do is add clauses to this set H. And of course, when you start, SAT can be anything, and I'm going to show you some examples. And then while you find satisfying assignments for this set of clauses, what you do is you find which ones are fixed. So H is defined on a set of variables U. This is meaning if the feature is now can take any value or if it's still fixed. So 1 is it can take any value, 0 it's still fixed. So these are the fixed features, and these are the features that can take any value. And then what you do is you see if you can find a CXP, a contrastive explanation, given the set S. And so if you can, then you can extract a CXP and you report it, and then you find a way to block it. And again, you could block it in other ways, but this is just a proposal. Otherwise, if you don't find the CXP, that means you can only find the XPs. So you are going to find an AXP, report the XP, and then you find a way to block it as well. The condition is that the way you block one and the other need to be different. Okay. And so let me try to show you an example of a decision tree. And I have more things to say about decision trees, but anyway, let's see how this works. So this is how do we do this? Essentially, the idea is that so when we start we don't have any clause, and so we could have any assignment. So let's assume we say all features are going to be universal. So and they can take any value. So the question is, if they can take any value, can I change the prediction? And the answer is yes, we just pick this path or this path or this path. So the answer is 1. And so what we do from the previous slide is that we extract the CXP, which, as I said, could be 3 or 5. Let's say it's 3. So I need to find a way to block it. And if you recall, this is where I am blocking the CXP. Okay? And so I block it. This means I cannot repeat this assignment again. Well, the point is that I cannot repeat U3 equals 1 again. So I call the SAT solver again, and it gives me something that respects that constraint. So, so this one is now fixed. I cannot make it universal, but I can still, if this one is fixed, I can still change the prediction here or here. Okay, and so I extract another CXP, which in this case will be 5. I block it, and I continue. So this means that for the future, now I cannot have 3 and 5 equals 1. So for example, the solution is 1, 1, 0, 0, 0, 1, 0, sorry. And so in this case, so this means that the fixed features are 3 and 5. And so now if I fix 3 and 5, for sure I cannot get to 0. So I need to extract an AXP. Yes? I block it, and if you can immediately see that this is the clauses that I now have, and this set of clauses is now inconsistent. So if I go back to the algorithm, this means I terminate. Okay. So this is how the algorithm in general works, and it works with any type. Notice that the operation does not depend on the decision tree. I'm just using the decision tree to illustrate how this is being done, but I really don't care about the classified itself. Okay. And now you could say, oh, well, but you started with 1s. What if the SAT solver was giving you 0s to start? It doesn't change anything. Well, the order in which you do it will change, but that's it. So you could say, well, I'm going to fix all the features to start. Instead of making them universal, you fix all of them. And that's fine. the set of fixed features is now huge, that's fine. You cannot find a CXP because you are fixing all the features, so you extract an AXP and you block it. And then you take it from there. It's the same approach. Okay, so again, you block it, and then for the future, you cannot have both one. So for example, you could have 3, 1, and that the other one has to be 0, and so on, and so on, and so on. Okay, any question? Okay, now the point is that I illustrate this with the decision tree because again, it's much more appealing to us human beings. I could do this with a neural network, but it would be much less easy to understand. So the point is that the decision trees are much easier to analyze than what I just showed. And so we can do the following exercise. So given an instance, we are going to create, I think this is a typo, I will fix it. So for each path, we are going to look at paths that have a prediction that is different from my prediction. And so for that path, PK, let IK denote the features that have literals that are inconsistent with my point in feature space. So what I'm going to do is I pick the features, I put them in this set I. And then what I'm going to do next after doing this exercise is I remove from I the sets that are proper subsets of some other set. Sorry, I'm going to remove the sets that are a superset of some other set. Okay, and so we can prove that this set, the resulting set I, is a set of CXPs, and so the algorithm runs in polynomial time. Okay, let me see if I can, and of course this is just for CXP. So how do we do it for abductive explanations? Well, we just run a standard dualization algorithm like Kashian's and Fredman's algorithm from '96. The interesting point here is that we know that the hypergraph we start from is polynomial size. So we can do it except dualization. Again, of course, we can have an exponentially large number of abductive explanations, but the hypergraph we start from, we can compute, and it's polynomial size. Okay. So, and we know for sure that as we start computing minimal eating sets of the hypergraph, it's going to be, each one is an abductive explanation. So let me show you an example. So notice that as I showed in the previous slide how you do enumeration in general. So here is for decision trees. So let's pick this path here. So which feature is inconsistent with my instance? It's just 3. To get here, only this one would have to be inconsistent. I don't care about the other ones. Okay. So if I change this, if I keep these ones and I change this one, I get 0. For this one here, the only one interesting one is 5. So this is the only one that would be, to get here is the only one with inconsistent values. Yes? And finally, for this other path here, I would have to X2 would have to be inconsistent, and X5 would have to be inconsistent. So I put 2, 5. Now, 2, 5 is a superset of 5, so I drop it, and so I just keep I1 and I2, and this means this is one CXP and this is another CXP, which we saw in the previous example as well. And so if I do minimal eating sets, I get 3, 5. That's my abductive explanation in this case. Okay. Any questions? Okay, so if you don't have questions, again, this is how what I showed was a general algorithm we can use in any case. I showed you for decision trees because it's much simpler, but I could use it in any other case. And then I showed that for some, in this case for decision trees, but in some other cases, we can find dedicated algorithms which are going to be much more efficient, like in this case. Okay. So let me talk about feature membership. So let's first talk about what is the feature membership problem. Suppose you have an instance as usual, and you have a sensitive target feature T. So an example of a sensitive feature would be, well, can we make a decision based on gender, age, race, health condition? And the question we are interested in answering is, if given my prediction, suppose it's a bank loan that was declined, does there exist an abductive or a contrastive explanation that includes the feature? So this is the feature membership problem. So this is important because if I'm in a bank and a client just got his bank loan declined and he asks, well, is it because I'm in poor health? I would like to be able to tell him no. your help was not used for making a decision. And so that is the feature membership problem. Okay. So let's see a concrete example again. So this is the standard example 00101. And from what we already saw before, we know that for features 3 and 5, the answer to feature membership problem is true, because we know that these features are included in the only abductive explanation and in the contrastive explanations. And for 1, 2, and 4, the answer to the feature membership problem would be false. Yes? Any questions?
Yes. So
yes.
To understand, so this problem of feature membership problem, how is it related to the problem you mentioned earlier about the redundancy of features?
Well, it's different because for a redundancy, in this case, it's the same, of course, because it's a very simple example. But redundancy, for a given path, for example, you could conclude that 3 is redundant, but it could occur in some other explanation. Okay, and so it's not the same thing. So here we are asking a question. So redundancy with respect to well, we are computing one explanation, just one, and so by doing that we remove redundancy. Membership, we are looking at all possible explanations. Okay.
Thank you.
So we have some complexity results. So we have bad news and good news. So the bad news is that for DNF classifiers, it is sigma 2p hard. And so this means we can solve the decision problem with, well, we have shown actually membership recently, so we can solve the problem with a 2QBF solve. Now, there are consequences to this result. So if you want to reason about neural net or random forest or boosted trees, because you can encode the DNF classifier with them, this means the FMP, the feature membership problem, is also sigma 2p hard for this in these cases. So this means you need to be able to solve a 2QBF formulation efficiently. And that can sometimes be problematic. So we have to keep this in mind. What we also showed is that for decision trees, membership is in P. Okay. And it's more interesting, the problem is in NP if we can compute either an abductive or a contrastive explanation in polynomial time. Okay, so let me clarify how this works. So the first claim is that
sorry, João, could you repeat the claim? The last one.
So I made 3 claims. So sigma 2p hard for the very simple DNF classifiers, and so this impacts a large number of other classifiers. It is in polytime for decision trees, and it's in NP, non-deterministic polynomial time, if you can compute an explanation in polynomial time.
Oh.
Okay, let me. It's easy, but of course we need to see it first and then say that it is easy. So let me start with the first claim. Well, the first claim I'm going to argue here. So FMP is in P for this polytime for decision trees. So what we can do is like this. We know that we can compute all the contrastive explanations in polynomial time. We talked about that. So we just have to go through the paths in the tree, remove the supersets, and what remains are the contrastive explanations. That we can do in polynomial time. And so now we check whether the target feature we are interested in exists in some contrastive explanation. If it exists, then the answer is yes, otherwise it's no. And this runs in polynomial time. Yes? Now the second claim is that FMPs in non-deterministic polynomial time, if we can compute one objective explanation, is in polynomial time. So, of course, because it's non-deterministic polynomial time, we start by guessing the set. And we guess the set that contains the target feature. And then, because computing one explanation is in polynomial time, we check in polynomial time that X is a weak XP. And then for each feature J, we check in polynomial time that taking out the feature is not a weak XP. Because we have monotonicity. So the overall algorithm runs in polynomial time. Is this? I hope this is clear. I think it's quite easy. And again, notice that you could say, but from a complexity perspective, is this important? Well, it is important from a practical perspective because now we know which type of tools we need to use to decide feature membership in these cases. Before we did not know. Okay, and the same here. So here it's very easy. It's in P, so it's easy, much easier. Any questions? Okay, so you could say, are these the universe of queries that are explainability queries? And the answer is, well, there are many other queries that people have looked at. So there is recent work by other teams on mandatory forbidden features for a given class. So I aggregate this with what I call class queries, and there are the necessary features for a class. So these are one universe of queries, and there are another universe are explanation queries, smallest, which I talked about during my talk already, finding one, which we talked about, and finding one CXP, which I talked about also. Okay, so there are some complexity results also by these other teams. So polynomial, most of these queries are polynomial time for decision trees. Again, decision trees are extremely amenable to reasoning, and other models are not. So all of these queries are computationally hard for a large range of other classifiers, decision lists, random forest, twisted trees, and so on. So again, this gives us pointers to what we can do and what we cannot do with these classifiers, and which techniques we need to use to solve them in practice. Okay. Do you have any questions? Okay. So let's.
I have a question. So, is there any relevant class of queries for which the decision tree is not in polynomial time, let's say?
Well, not well. In my definition, yes. So let me go back. That's a very good question, because again, this depends on which queries you are talking about. So we can compute all the CXPs, the contrastive explanations, in polynomial time, but we do not have a polynomial delay algorithm for AXPs. So this algorithm here, if you recall, is quasi-polynomial, but it's not polynomial. So you could say, is this the best we can do? Well, I'm not so sure, because what we are doing is reducing the problem to this problem. There could be a better way to do objective. I don't know. So this is one example of an open problem for which, do we have polynomial delay in this? I don't think we do, but it's not proven. What I argued is that I can reduce enumeration of AXPs to dualization algorithm of Friedman and Kashin, and so it's quasi-polynomial time, but that's it. And so yes, and again, this is just proposed queries. Yes, there are proposed queries that you could actually, we have devised more queries which I'm not going to talk about because we are still working on them. Okay. So let's talk about another topic, which is a probabilistic explanation. And you could ask why we care about this, and I will try to make a case for this. So, so what happens is that sometimes the explanation size of explanations can be too large for what a human decision maker can understand. So there are papers from the 60s claiming that the cognitive limits is 5 or 7. So 7 plus or minus 2, I think that's the title of the paper. So essentially, if you have an explanation of size 50, well, then we need to find ways of making it more interpretable or easier to grasp for a human decision maker. Okay. Now, people have proposed to compute the smallest explanations. What we observed is that in practice, they are not much smaller than irreducible explanations. So there could be a difference, but they are not. So if you have your subset minimal explanation is size 50, it is very unlikely that your smallest explanation is size 5. Usually, we don't see that in practice. And so the idea of probabilistic explanation is to trade off. So we compute explanations of smaller size, but we cannot guarantee the same rigor. Okay, And so that is what people, there has been a lot of activity in this area by different groups. So what people are trying to do is, how can we do this? So let me try to give you a definition and then summarize some of the results that exist. So the idea is that we, instead of computing an abductive or a contrastive explanation, now here we are essentially talking about abductive explanations. And so we want to find a set of features such that the probability of getting the class right, given that your points in feature space are consistent with your instance on the points on the features given by set X, that this probability is greater than delta, some delta. So if delta is 1, then if you want the probability, so this essentially are saying that I want an AXP or a weak AXP. So this becomes interesting when delta is less than 1. And so the question is, how can we compute this? Okay. And so we can define a weak probabilistic abductive explanation, which is, again, given by that the definition up there. And so what we can do is reason in terms of these sets. And so what should we compute? The first works in this area covered cardinality minimal. What we have done is to talk about subset minimal, because again, this relates with abductive explanations as we define them. So let me summarize the results that have been obtained. If you have a Boolean circuit classifier, this is a very restricted class of classifier, computing one smallest probabilistic abductive explanation is NP to the PP hard. So this is a result from last year. Okay. So this is not interesting because, again, there are reasons for this type of complexity should in general not be expected to scale. So this is problematic. So in general, this is going to be a problematic problem. For decision trees, what we proved is that what is known is that finding one probabilistic abductive explanation is in NP. So it's and there is a proof now that it's NP hard. And so this is a good result because essentially this means we can devise logic encodings and use SMT or SAT reasoners for this. And we have done that actually. And what we also showed is that, so the difficulty, let me go back. The difficulty is that this definition in general leads to non-monotonicity. And so this makes the problem of computing subset minimal or smallest much harder than what I've talked about until now. And so what we propose is forget about non-monotonicity, so essentially approximate weak probabilistic abductive explanations, and we show that we can compute those in polynomial time. Okay, and we show that in practice the quality of the approximation is very, very good. Okay, so the point is that the fact that we have non-monotonicity is not that important in practice. So that's one result. And for naive-based classifiers, we propose the dynamic programming approach for computing probabilistic abductive explanation. So the point is that the dynamic programming approach, the size of the table can grow exponentially with the size of the NBC. We don't see that, but it can happen. And just to highlight that there is a recent Arner's results by a group in Chile, which this is part of, this result here is part of. Okay. So again, as I said, there is a lot of interest because this is probably a necessary trade-off to convince decision makers to use fairly rigorous explanations. So an open question is a general approach for this problem, which again, I think it's fairly fascinating. I don't have a clue on how to do it yet. Okay. Any questions? Okay, if not, let me talk a little bit about a few more topics and wrap up. So there are, you could say, is this it in terms of formal explainability? And the answer is no, there is much more to it. So first, I will mention links with fairness and robustness and model learning. So in terms of robustness, and robustness is how a machine learning model is insensitive to predicting something that is very different with a small change on the input. And so we show there is a tight, well, the robustness is related with adversarial examples, and we show there is a tight link between objective explanations and robustness. Okay, so that's one example of a link between the two areas. In terms of model learning, there is a lot of activity on learning interpretable models, a lot of work by different authors and ourselves as well. As I showed during the talk, learning interpretable models is not the final answer. We need to explain these interpretable models, but still, explaining decision trees is much easier than explaining a neural network, so this could be important as well. And finally, in terms of fairness, we looked at one concrete criterion, fairness through an awareness. And we show that we can assess bias both on the data set and on the classifier. And this relates with membership, of course, a membership problem. And the bias on the classifier is related with explanation. So that's why it is related with membership. So if there are features we want protected, we can use membership to make those decisions, for example. Okay. There are many other topics I could not cover in the talk, so I will try to mention some of these topics. What we noticed is that we need to account, most papers have not, in most of our work we have not account for input constraints. So let me give you an example. Suppose you have a feature which is gender, male, female, and you have another feature which is pregnant, yes or no? And we noticed at some point that the counterexamples we were finding to show that some explainers were incorrect were of the type a male that is pregnant. Okay, and so when we get the data set, we don't have this information, and so we need to find a way to get to identify the input constraints that we should use when reasoning about explanations. And so either those constraints are given to us, number one, or we can try to infer them. And so there is recent work on either using input constraints or inferring input constraints to essentially change the type of explanations that we are going to compute. So that is one area of work. Another area of work is the use of surrogate models, which, for example, this is what Lime and Sharp are doing in non-formal explanations. So what is the idea? The idea is as follows. Until now, for the last 3 years, we have achieved several important results, I think, but we have not been able to reason about neural networks. So what a different group has proposed was to do not explain the neural networks themselves, but instead approximate the neural network with a simpler model, still complex, like a random forest. In this case, they proposed using a random forest, and then compute explanations for the random forest. Okay? So this is promising. My criticism was that they never validated against the original model. So we don't really know if the explanations are of good quality for the original model. Right? But in any case, again, this could be crucial to reason about very complex neural networks. Another criticism and a topic of research is, well, most of the work I showed during my presentation is literals use equality. So a feature equals some value because that's what we are given. Now that is, of course, if the classes, the features are categorical, this is fine. But suppose, and someone asked the question, what you could have real valued features. So is it interesting to say that some feature equals 2.253? Yeah, that's not really the case. And so the idea is that we can try to generalize the exponential literals. We have done that for decision trees in recent work. It is open how you do it for other types of classifiers. Someone also asked me the question about are these explanations local or global? And I said they are localized, but they hold globally. But if we want to relate with what other tools are doing in terms of even assessing the quality of what they are doing, we should be able to compute more localized explanations. So we could have a measure of distance from the instance we are interested in. And so we can compute objective explanations subject to not being too far away from the point in feature space. Okay, so that is another area of work, which I mentioned in the notes that I prepared. And finally, and this is an area that has been around informal methods for many years. So when people, so I showed you algorithms and I convinced you arguing that they are correct, right? And everybody, I would assume everyone agree that they are correct. So the fact that the algorithms are correct does not mean that the implementation itself is correct. And if you're going to implement some sophisticated reasoner, the likelihood of having bugs is not non-significant, so it could be important. And so one area of work I started working recently with a colleague is how can we certify the explanation results that we are computing? How can we certify that an objective explanation is an objective explanation? How can we certify that a contrastive explanation is a contrastive explanation? How can we certify that age is not used in some prediction, and so on? Okay, and so this raises a large number of challenges, and I would like to believe this is an important topic for the near future.
May I ask a question, João?
Sure.
Yeah, you mentioned before you move to the next slide, I mean, you are mentioning these localized explanations. I mean, yes. As you, of course, you know, I mean, there is also some work on explanation based on scores, right, that assign numbers to yes. feature values. And so in order to reflect their importance, I mean, for the label that you get, right? So I'm wondering if this localized explanation in the way that you are describing them here is related to those score-based explanations. Have you thought of?
Well, that's a very interesting question. Thank you. I thought about that. So I thought, how can I make that? How could we make that link? So going from so because essentially we are saying feature in, feature out. What you are saying is that some others have done is importance of feature in general. That is of course very interesting. I could not make the connection yet. So so localized explanations are not that. Essentially the idea is that you don't really care about the behavior of the classifier if it's too far away from your point in feature space. What you are suggesting is different, is how can I attribute a weight to features? Because that might, humans might be more amenable to that information. There is a gap there. Yes, I accept that is a gap. There is a gap because we could not yet, I discussed that with some collaborators, we could not find a way to model that information. But yes, so that is something that if someone could make a proposal, it would be very interesting.
Yeah, I mean, because if you are already introducing something like a metric here, I mean, you might end up, I mean, making a connection, I mean, with score-based.
Yes.
I mean, that's I mean, it's just a thought. I mean, maybe something to explore there.
Yes, as I said, well, I could not find a way to formalize that. Maybe it's my again. I tried a few times. I could not really find a way. Again, the year is moving very quickly, so we have been looking at other topics. This has been on my mind since almost the outset, and I could never find an easy, elegant way to do it. But yes, again, I think that if someone could make a proposal in that direction, it could be very interesting.
Thanks.
And again, so I talked through for a long time about machine learning explanations. What is there? Well, several things. So first, there are tight connections between machine learning explanations and other areas. So model-based diagnosis and detection, I showed you several connections. I mentioned in passing several connections throughout the talk. There is a lot of work on explainability in AI planning, also in optimization and problem-solving problems. And again, given the legislation that we have in Europe, it seems clear that explanations for any of these problems and other problems will be important as long as you have some sort of algorithmic decision making. So I don't see any way around that. And the techniques, sometimes they appear different, but as I try to show during my lecture, is that there are, for example, in model-based diagnosis, people these days use them with other name. In optimization, people are using MUSs, the same way in problem solving, smallest MUSs, for example, and so on and so on. So in AI planning, the same. So they came up with a different name, but the definition is exactly that of an MUS. So, and of course, what we are doing is essentially computing MUS and MCS. So that all these areas are extremely related, and the type of approach used for explaining very different observations is very similar. Okay, so to conclude, so I spent some time at the beginning of the lecture talking about the limitations of widely used XAI approaches. And when I say widely used, I mean really widely used by a huge number of people are using this. So I hope I convinced you that if you use a tool like Lime or Sharp or Anchor or similar tools, you are going to get incorrect explanations. So they will be valid for different predictions, which in my opinion doesn't make any sense, but it's just my opinion. And again, I focused on model agnostic methods, but similar limitations have been reported when you use saliency methods, maps for neural networks, for example. So that is one component. The other component is that for intrinsic interpretability, the explanations that you get can be very redundant. I focused on decision trees. We have results for others like decision lists and so on. Right? And so essentially, I don't see a solution. These approaches as a solution that you can use in sensitive areas like high risk applications or safety critical applications. So essentially, the bulk of the talk was about logic-based formal explainability. I started with a logic rigorous definition of explanations. So I introduced abductive, I introduced contrastive explanations. I showed there was a duality relationship between them, which we can use to compute other explanations. And so this is interesting because essentially, even though it's more philosophical, this link shows there is a connection between answering a why and why not question in general. I mentioned also in passing there are links with model-based diagnosis, and I talked about other problems that are very important, like navigating the space of explanations, and this is enumeration, and finding whether sensitive features can be used for explaining some prediction. And I also mentioned a lot of recent topics of research. Enumeration is still ongoing because we are only seeking better, more efficient algorithms. Deciding membership of features in explanation. So there is a gap. So we don't have we did not present a general algorithm for probabilistic rigorous explanations. What I showed is that it's at the inception. So we know that we can reason about decision trees and naive Bayes, but there is a lot we don't know. We have complexity results, but we don't have algorithms. So that in practice we can compute these explanations. And again, there are, of course, questions about the complexity of explainability in other settings. And finally, going back to the first bullet, which I did not mention, so I showed a lot of progress. I think it's a lot of progress, but it's also clear that there are important limitations still. So if you give me this huge neural network to explain, I cannot. And I cannot because I don't have efficient algorithms, and no one can. No one on the planet can. And so that is a big area of research. So what techniques can we devise to improve the efficiency of reasoning about abductive and contrastive explanations? For example, in the case of neural networks. And so one way, of course, is I mentioned that in passing, is to use surrogate models. But there, as I said, we don't really know the quality of explanation. So one area would be to improve the quality of surrogate-based explanations. The other area would be to improve the reasoning capability of reasons that we are using in the case of neural networks. And that's it. I would be happy to take additional questions that you might have.
I have a very basic question about definition explanation in your talk. So